These are your notes for Unit 4, Day 6 of Calculus. If you would like to see the warm-up, the review question, or any homework questions we covered in class today, just look at the finish notes. So today we are going to continue talking about integration and U-substitution. And today we're going to talk about how to integrate functions where you need to use U-substitution, and they are definite integrals, meaning that they have bounds on the integrand symbol. All right, so review of integration by substitution. So let's just review these problems. So if we want to integrate 3 minus x to the 10th dx, this would be an inside function type of U-substitution, where the inside function is 3 minus x. And then remember, you need to be careful because the derivative of this isn't just 1. It's actually going to be negative 1 and then dx. And so the original problem has a dx, but it doesn't have a negative dx. So we're going to divide both of those by negative 1. And so you get negative du is equal to positive dx. So I'm going to substitute negative du in for the dx, and I'm going to substitute u in for the 3 minus x. So I'm going to pull out the negative from the negative du to the outside, and then I have u to the 10th, and then that dx will become negative du with the negative on the outside, and then du. And then when I find the antiderivative of that, I get u to the 11th over 11, and then plus c, and then substitute back in for the u, so you get negative 3 minus x to the 11th over 11th plus c. And that would be the antiderivative of that integral. All right, on the next one, we have 4 times cosine 3x. I'm going to let u be the inside function of 3x. So du is going to be 3 dx. Again, 3 is not part of the problem. That 4 is just a coefficient, so I can pull it to the outside. So now I have 4 times the integral of cosine u, and then times 3 dx. So that 3 can also be pulled to the outside. So now I have 12 times the cosine u, 12 times the integral of cosine u du. Now the antiderivative of cosine is sine, so now I have 12 times sine u plus c, and then plug back in for u, so I have 12 sine 3x plus c would be the antiderivative of that function. So that's a review of integration by substitution. These are both when u would be an inside function. All right, so we've got some more inside function ones. So this would be the same thing as the integral of sine x, that whole quantity cubed, then cosine x dx. So u in this case would be the inside function of sine x. The derivative of sine x is cosine x dx. And so this is just a replacement. So this would be u to the 3rd du. And when you integrate u to the 3rd, you get u to the 4th over 4 plus c, and then substitute back in sine. So you get sine to the 4th x over 4 plus c would be the antiderivative of that original function. And on the next one, we have x to the 3rd over 1 plus x to the 4th all raised to the 1/3 power. So u could be the inside function of 1 plus x to the 4th. And so du would be the derivative of that, which would be 4x to the 3rd du. We have an x to the 3rd, 4x to the 3rd dx. So we have the x to the 3rd dx, but not the 4, so we'll divide both sides by 4. So I have 1/4 du equals x to the 3rd dx, and so when I replace, I get du over u to the 1/3 power. I'm going to rewrite this as u to the negative 1/3 du. And so if I integrate that, add 1 to the exponent and divide by the new exponent, so I'd get u to the 2/3 divided by 2/3 plus c. When you divide by a fraction, multiply by the reciprocal, so it'd be 3/2, and then replace the u, 1 plus x to the 4th to the 2/3 power plus c. And so again, those are 2 more examples of u substitution where u is an inside function. All right, why don't you guys pause the video and try these 2 and then check your work against the finished notes from class today. All right, U-substitution and definite integrals. So there are 2 options on how to do these problems. We can do it exactly like we've been doing them yesterday in the beginning of class today, but then just forget about the bounds at the start of the problem. So option 1 is you use the bounds as the last step. So the very last step, you're going to use the bounds. So before then, we just kind of forget that the bounds are there. So we're going to forget the bounds are there. And then we just have 8x and then 4x squared plus 1 squared dx. So I'm going to let u be the inside function. So u would be 4x squared plus 1. So the derivative of that would be 8x dx. And notice that's the numerator, so we're good. So now I have the integral of du over u squared. And if I rewrite that, I get the integral of u to the negative 2 du. So when I integrate that, I get u to the negative 1 over negative 1 plus c, or negative 1 over u, and u is 4x squared plus 1. And now, instead of the plus c, so now we're on the last step. So now we're going to take those bounds, and we're going to use them on the very last step. So now we're going to integrate this between negative 1 and 0. So plug in 0, plug in negative 1, and subtract. So this will be negative 1 over 4 times 0 squared plus 1, then minus negative 1 over 4 times negative 1 squared plus 1. And so we get negative 1 plus 1 over 5. So we get negative 1 plus 1/5, which would be negative 4/5. So that's option 1. If you want to just do it like we normally are doing it, option 1 is you just kind of forget about the bounds until the last step. So you do the normal u substitution integration, and then use the bounds on the last step. Option 2 is you can change the bounds or the limits to u bounds. Okay, so we're going to change them to u bounds on this step right here. So that's the step where we would change them to u bounds. So we would do the normal problem. So we want to integrate from negative 1 to 0 of 8x over 4x squared plus 1 squared dx. So we're going to let u be 4x squared plus 1. Du would be 8 dx. And so when we replace, no bounds right there, and I would get du over u squared. So at this point in time, we're going to change the bounds. So the original bounds were x bounds. So we have x equals negative 1, and we have x equals 0. And now we're going to change them to u bounds. And so we need this relationship right here. U is equal to 4x squared plus 1. So my bounds are going to be, so to change x equals negative 1 into a u bound, we have u equals 4 times negative 1 squared plus 1. So that u bound is going to become 5. And then for that top u bound, you're going to plug 0 in for u. So u equals 4 times 0 squared plus 1. So that top u bound will be 1. So my two u bounds are 1 and 5. So now I'm going to integrate this between 5 and 1. And so we've already done that antiderivative. The antiderivative, and again from 5 to 1, and this would be u to the negative 2 du. So this would end up being, add 1 to the exponent, divide by the new exponent, you would get u to the negative 1 over negative 1 between 5 and 1. Now notice, we don't have to substitute back in for the u at this point in time because we've changed the bounds. So I don't need the x's anymore. The x's are completely done because we changed those bounds. So again, this is going to be negative 1 over u between 1 and 5. So now when you plug in, you get negative 1 over 1 minus negative 1 over 5. And we get negative 4/5, just like we did before. So you have two options when you have definite integrals and you are going to have to use u substitution. So option 1, you can handle the problem exactly like what we were doing before and just forget about the bounds until the last step. Or option 2, you can change those two limits of integration or the bounds of integration to u instead of x. So let's look at this next one. So we would let u be the inside function of x squared minus 1. So du would be the derivative of that, so 2x dx. There's no 2, so we're going to divide by it. I get 1/2 du equals x dx. And so I'm going to pull out that 6 and pull out the 1/2, and that would become 3, and then the integral of u squared du. So if we forget about the bounds, then I would get 3 times u cubed over 3 plus c. So this would be u cubed And then we're going to replace the u with x squared minus 1, and then that would be cubed. And now we use the bounds. So now I'm going to take those bounds and use them. So I'm going to evaluate this between -1 and 2. And so I would get 2 squared minus 1 cubed minus -1 squared minus 1 cubed. And so I get 3 cubed, so 27 minus 0. So without changing my bounds, I would get 27. Or on this step right here, we could change the bounds. So we have the integral of 3 u squared du, and now I'm going to change the bounds. So the original bounds were -1 and 2, so those are my x bounds. And if I want to change them into u bounds, I have to use this formula right here, x squared minus 1. So if I do 2 squared minus 1, I get 3. And if I go do -1 squared minus 1, I get 0. So these bounds are going to be 0 and 3. So if I integrate this, this would be 3u cubed over 3. And I want to integrate that between 0 and 3. And so this is just going to be u cubed between 0 and 3. So this will be 27 minus 0, which is 27. So again, either option is okay. You can just integrate like normal and then use the bounds as the last step. Or you can change the bounds to u bounds and then not have to plug back in for x when you're done. And that's how you can deal with u substitution and definite integrals. And so whatever option you like better, you can use. All right, let's look at this one. So this one's a little bit different. Normally, well, I guess it actually would work the way we would want it to work. So if I rewrote this, you've got two options on what you want u to be. You could let u be tangent x, because what's the derivative of tangent x? It's secant squared x, and that's there. Or you could let u be the inside function, secant x, and the derivative of secant x is secant x tangent x, which is also there. But I'm gonna let u be tangent x because I can see the derivative right away. So I'm gonna let u be tangent x. So then du, the derivative of tangent x, is secant squared x dx. So now I'm just going to make this u du. And the antiderivative of u is u squared. So I have u squared over 2 plus c. And then plug back in. So u is tangent. So I have tangent x squared over 2. And then I want to evaluate that. Now I'm going to use the original bounds between 0 and pi over 4. So 0 to pi over 4. And so now I have tangent at pi over 4 squared divided by 2 minus tangent at 0 squared divided by 2. Tangent at pi over 4 is 1. 1 squared is 1. So this is 1/2 minus tangent at 0 is 0. And 0 divided by 2 is still 0. So that's just going to end up being 1/2. All right, let's look at the next one. We've got a e with the weird exponent, so we're probably going to make u be the weird exponent. So u is going to be the square root of x, which is the same thing as x to the 1/2 power. So du would be the derivative of that, which would be 1/2 x to the -1/2 dx. I'm going to rewrite that. The x to the 1/2 would move down to the denominator with the 2, and x to the 1/2 is the square root of x. So it'll be 1 over 2 root x and then dx. So notice the 1 over 2 root x dx is right here because that 2 root x is in the denominator. So that whole du is there. So this is going to be the integral of e to the u du. And if I integrate e to the u, I get e to the u. And then plug back in. So this would be e to the square root of x. And now I'm going to use those original bounds, 1 and 4. So I'm going to evaluate this between 1 and 4. So this would be e square root to the square root of 4 minus e to the square root of 1, which would be e squared minus e to the first. And that would be that definite integral. All right, let's look at these two. So we want to integrate from 1 to 0 of 3 over 3x minus 2. So I'm going to let u be the denominator, 3x minus 2. So the derivative of that would be 3 dx. And notice that's the numerator. So this is just a straight substitution. So this would be 1 over u du. And the antiderivative of 1 over u is the ln of u, and then plus c. And so plug back in. This would be the ln of 3x minus 2 in absolute value, and then use those bounds between 1 and 0. So if I plug in 0, I would get the ln of 3 times 0 is 0, minus 2 is negative 2. So it would be the ln of the absolute value of negative 2 minus the natural log of 3 times 1 is 1, minus 2 is 1. So minus the natural log of 1. So this would be the ln of 2 minus the ln of 1, and the ln of 1 of 0. So this is just going to be the natural log of 2. All right. The next one is one of those, I wouldn't call it a trick problem, but it's one of the ones that once you recognize what's happening, you'll be able to see it every time. So I'm going to pull that 2 to the front, and then I'm integrating from 1 to 2, and then I'm going to write it as the ln of x times 1 over x dx. So I'm going to rewrite it like that, because maybe then it'll be easier for you to see who u should be. And remember, once you pick u, you want to see the derivative of u there. So what's the derivative of ln x? It's 1 over x, and that's there. So I'm going to let u be ln x, and then the derivative of that is 1 over x dx, which is part of the problem. So we're good. This is going to be just a straight u substitution problem. So this would be the 2 times the integral of u du. And when you integrate that, you get u squared over 2, and then plus c, those 2's will cancel. And so you just have the ln of x, once you plug back in, squared. And now I'm going to use those bounds. I want to evaluate it between 1 and 2. So this would be the ln of 2 squared plus the ln of 1 squared. The ln of 1 is 0, so this is just going to be the natural log of 2 squared. And so that is u substitution with definite integrals. Your homework is your worksheet.